Hello, and welcome to a presentation of PotatoChip, an architecture developed in fulfillment of requirements for CSCI E93 computer architecture. My name is Rajesh, and I'm going to be going over some details of this architecture in this presentation. First, I'll present an overview, followed by some features of the assembler, the emulator, and then demonstrations of a program running in emulation, as well as on hardware on the FPGA. The potato chip architecture consists of 32 32-bit general purpose registers. It has a separate dedicated program counter register, as well as a dedicated instruction register that's not visible to the programmer. Instructions to operate on data less than 32 bits are also available, such as moving an immediate value to any arbitrary byte of the 32-bit register. The architecture also has a 32-bit left and right unsigned barrel shifter, which supports any arbitrary shift amount. It also supports 32-bit saturated addition instructions, which add and then, depending on the carry-out flag and the sign bits of the input operands, will decide whether or not to saturate the value rather than allow it to overflow. The architecture also has single instructions to branch based on comparison against 0, such as branch when equal to 0, branch when not equal to 0, and so on. Assembler features. The potato chip assembler supports the following directives. The first directive is .define. This allows the programmer to define a constant value mapped to a label. For instance, here I've mapped -3 to the constant -3, and this label can then be used in code rather than having to use the numeric value. This is particularly useful when dealing with memory mapped register values, where the numeric value might not be as meaningful as a label that describes what that numerical value is. The second directive is .word. .word consists of a label, :.word, followed by comma separated values. For example, label : .word 1, 2, 3. This reserves memory for 3 words, starting at the address pointed to by this label, and then each integer here is treated as a word, which in this architecture is 32 bits. Similarly, .hword, standing for half word, and .byte, standing for byte, all reserve memory for these integers held in 16-bit in the case of half word and 8-bit precision in the case of .byte. The alignment requirements for .word and .half-word are maintained and ensured by the assembler. The .word is always aligned to 4 bytes, whereas the .half-word is always aligned to 2 bytes. .string is similar to .byte, but instead of a comma-separated list of integers, the programmer specifies a string that is enclosed by double quotes, and these are translated to ASCII bytes, and memory is reserved for the entire string, plus a trailing null character that is inserted automatically by the assembler. Listing file. When we assemble a program using the potato chip assembler, an optional listing file is also generated. The listing file has the following format: a PC address in hex, colon, the encoded instruction at that address, and then the raw line from the assembly file which was translated to this encoded instruction. The utility of this listing file is to debug a section of code when running on hardware. When we get a PC value or the contents of the IR and we want to make sure that the instruction did what it was supposed to do, we can use the listing file to look at what instruction that IR value refers to, or what instruction is supposed to be at that PC value, and then we can use that information to debug our program. This is another feature of the assembler called a map file. A map file is just a debug file that lists key value pairs of all labels that were defined in the assembly program and their corresponding values. In case of constants, the corresponding value will just be the constant integer value, which was programmed using the .define. But in case of actual labels like putInt, which correspond to an instruction address, then the PC address at that label is included in this file. Now, using this file, when running the program under emulation, we can set breakpoints using the label names directly, rather than having to find out the numeric value of the address corresponding to that label and then using that to set breakpoints. Emulator. The emulator supports a variety of shell operations, including setting, listing, and deleting breakpoints. The breakpoints are expressive, using label names directly as opposed to numeric address values. Also, there is a special display of modified registers at each step. For instance, here R1 was modified by the previous instruction, which is displayed here. There's also a disassembly of the instruction register contents in plain text for the programmer to easily follow where they're stepping through in the assembly program. Now let's take a look at a demo of the emulator in action. This is a demonstration of a program running in emulation using my emulator. The program is to multiply two 16-bit signed integers and then display them to the console through converting each digit to ASCII. The program has been written in assembly and assembled with my assembler to the MIF file. The assembler also produces a map file, which is a debug file that consists of key value pairs that map each literal label or constant used in the assembly program to a constant value or a specific address, which will be the contents of the PC when an instruction corresponding to that label is executed. We can use this map file to also set breakpoints in our emulator using the names of the labels directly rather than numeric address values. Let's take a look at a program running in emulation. We can first, using the emulator shell, display all available options using the H argument. These are the options. The first option is N, S, step, and start. These all are equivalent and can be used to step through the program one instruction at a time. The next argument is A, which can list all set breakpoints as a table. D or clear can delete or clear all set breakpoints. B, followed by a space delimited list of either numeric PC values, address values, or string label names, will set breakpoints at those specific addresses. C will continue execution until we hit the next breakpoint, and Q will quit the emulator. So let's step through the program a couple of times and take a look at what happens. We can see that with each step, the displayed PC is the first thing to be displayed. We also see that the encoded instruction has been decoded to plain text and is displayed here. Further, any general purpose register that was modified in the previous instruction, for instance, in this instruction R1 was written to from this immediate value, which we can see here, and those modified registers alone are indicated with a red color. So now let's set a breakpoint at the labels corresponding to the assembly subroutine putInt and long_mul. These two subroutines respectively display an integer to the console by converting each decimal digit to an ASCII value, and long_mul multiply is the subroutine to do the actual multiplication. Now that we've set the two breakpoints, let's use A to display the two breakpoints as a table. That's displayed here. This is the PC value and the corresponding label from the map file. Now if we hit continue, the program will continue execution. Let's provide some values for the two operands. And we can see that we've hit the first breakpoint at long_mul, and we can examine the contents of the general purpose registers. If we hit continue, we hit the second breakpoint at putInt, and we can also take a look at what's in each register here. And if we continue, the result is displayed and we are prompted for two more input arguments. Okay, now that we've taken a look at the emulator, let's look at the VHDL implementation of this architecture. The processor was implemented entirely in VHDL using generics wherever possible to ensure maximum reuse of components across the implementation. The state machine for the CPU sequencer is as follows. These are all of the available states that our CPU can exist in, and they're organized as follows. Those enclosed by the purple box correspond to memory subsystem finite state machine states to read a specific instruction from memory into the instruction register. Those that are enclosed by the red box correspond to memory finite state machine states. To optionally read memory to populate a GPR, this would be the states that we would have to go through in case of a load instruction. Those enclosed by the green box correspond to memory finite state machine states to optionally write a GPR's contents to memory. These are the states that we would have to go through to execute a store instruction. Finally, irrespective of which instruction we execute, we update the PC as appropriate, either by incrementing it in case of a regular instruction or by modifying it in case of a jump or a branch instruction. And once the values are committed to PC and any modifications to GPRs are done, we go back to reading the next instruction from memory using the PC value that's currently in the register. Any ALU operations will happen between when we read an instruction from memory and decode it to when we commit values to general purpose registers and the PC. The ALU is the backbone of the potato chip architecture and is used to implement almost all of the instructions. These are the operations available to the ALU, which takes an operation, which is an enumerated type, along with two arguments. Each of these are 32-bit quantities, and it produces an output from the ALU and a carry bit that can be used for things like saturation. The available operations are as follows. The first three, addition, subtraction, and negation, are done using an adder implementation, which is a ripple carry adder based on full adders that have been chained to 32 bits. The shift operation is implemented using the barrel shifter, in which case argument 1 is assumed to be a shift amount, and argument 0 is the value to be shifted. If the shift amount is negative, then we implement a left shift. If the shift amount is positive, then we implement a right shift using the barrel shifter. The next few operations, AND, OR, XOR, test, and equals, are implemented using logic. AND, OR, and XOR are self-explanatory, which are bitwise operations done on the bits in ALU arg0 and arg1. Test, however, is used to test whether or not a specific bit whose index is indicated by ALU arg1 is set in ALU arg0. So for instance, if ALU arg1 is 3, then test returns all ones if the third bit in ALU arg0 is set, and it returns zeros if that bit is not set. This is very useful for doing comparisons followed by a branch that looks at a register's value and then decides whether or not to branch based on whether it's 0 or not. The equals operator is just a comparison of the bits of ALU arg0 and arg1 and then sets the ALU out to all ones if they're equal and all zeros if they're not equal. Finally, the SADD is a saturated addition of bytes, which adds each byte in ALU arg0 and ALU arg1 and then saturates the results to signed 8 bits and assigns the result to ALU out. So this is implemented using byte adders followed by some logic for saturation. The logic for saturation involves looking at the sign bits of ALU arg0, each byte in ALU arg0 and arg1, as well as the carry out from doing the byte addition and determining whether or not we should set the resulting value to 7f, which is plus 127, or minus 128 if it's an underflow. If the conditions for overflow and underflow are not met, then we just copy the results of the byte adder directly to the corresponding bits in ALU out. So let's take a look at a demo of the multiplication program in action, which is running on the FPGA hardware. But before we look at the program, let's take a look at the debug capabilities of the hardware, and then proceed to look at the program running on the hardware. This is a demonstration of my FPGA's debug configuration. The slide switches, the push buttons, and the hex display are configured as follows. Slide switch number 17 and 16 are reserved for clock suspend and clock hold respectively. When clock suspend is turned on, then the clock that comes from the memory subsystem is suspended, And when clock 16 is turned on, the clock from the memory subsystem is held, and we can step through clock by pushing on clock step, which is connected to push button 2. Switches 11 down to 6 correspond to the clock divide limit. Switch 11 corresponds to the highest bit. Here I've turned on switch number 7, which corresponds to the highest bit minus 4. Switch number 5 corresponds to the PC. When I turn on the PC, when I turn on the switch and turn off all other switches, the hex displays will display my current PC value. If I also turn on switch number 4, then the hex displays will display my IR contents. If I also turn on switch number 3, then the hex display will display the current state of my CPU finite state machine as an integer. If instead I turn off these switches and turn on switches 4 down to 0 in any fashion, like so, then this, which is number 6 in binary, will display the contents of GPR number 6. Now, if we go back to displaying the PC by turning on switch number 5 and press on the clock step, we can see that we can step through our program as the PC increments. This is a demonstration of my final program for multiplying two signed numbers executed on the FPGA. I've programmed the FPGA with the MIF file generated by my assembler. Now, when I turn down the clock hold switch, we can see that the prompt to enter the first number is being displayed. Now, when I enter the first prompt, the prompt is also echoed on the screen. Now I get the prompt for the second argument. This too is displayed on the screen. The multiplication is done in hardware, and the result is also printed to the screen, which then proceeds to loop and then prompt for another set of two integers. Finally, I'd like to give my sincere and immense thanks to Professor James Frankel for his extensive hands-on support, including and up to the very last minute. His guidance and encouragement, which was really crucial for implementing all components of this project. TAs Alex and Daniel for their illuminating sections and very, very long office hours, which were extremely helpful to make progress. Classmates and peers for their helpful advice, conversations, and questions. And finally, I know it's always bittersweet to complete one of Professor Jamie's classes, but I hope we can all stay in touch and meet beyond this class as well. Thank you, and have a nice day.